And we are live. Uh, Hello, everyone. My name is Eitan Suez. Welcome to the Tetrate Tech Talks. This is a live stream that we are doing to YouTube and LinkedIn Live. What I'm showing to my right is a Tetrate Tech Talks landing page, which I like to sort of advertise the URL for, so that in case anyone wants to get at the links that we're going to be discussing and so on and so forth, you'll be able to get to them. My name is Eitan Suez. I'd like to welcome you to Tetrate Tech Talks. The date is Friday, May the 13th, a little ominous. And this is episode 6. These Tech Talks are a weekly live stream where we feature conversation with the guest, discuss tech, do technical presentations and demonstrations, and much more. Tetrate, of course, is the enterprise service mesh company, and our focus is on Istio, Envoy, Kubernetes, and related technologies. And this series of broadcasts was launched on April 1st, and this is episode 6. So this is all a relatively new effort. And I'd like to welcome you all, and feel free to say hello in the chat if you're on YouTube or LinkedIn. We have a guest who's going to give us a technical presentation for this episode. I'll be introducing him momentarily. And as usual, I'd like to start with sort of the order of the day, announcements, what goes on in the service mesh community, so on and so forth. So let's dig in to episode 6. So
I think we lost Eitan. Let's wait for a second until he comes back.
All right, I'm back. Can you hear me now? Yeah. All right. I really apologize. This headset is giving me a lot of trouble, and I've decided to just stop using it. Thank you, Adam, for taking over for me. Adam is our guest for this episode, and we'll see him in just a few minutes. So let's get back to the program. I'm going to share my screen one more time, and hopefully second time will be a charm and not third time. All right. So we're back here. All right, and so as I was saying, Tetrate Tech Talks is a live stream where the objective is to learn, share knowledge, get to know members of our community, and have plenty of fun. My name is Eitan Suez, and I would like to thank you for joining us. If it's the first time, welcome. If you're a repeat visitor, we thank you for tuning in. And again, don't be shy about saying hello in the comments and just letting your presence be known. Just a recap of where we are today, May 13th. Last week, we had a very interesting talk with another guest, Brian Sletton, on the subject of WebAssembly. If you missed that one, that past episode and all past episodes are recorded and available both on YouTube and LinkedIn. What else? Industry events, lots happening right now. I actually am coming to you from a new venue from Valencia, Spain, since in just a few days on Monday, the KubeCon EU conference is going to begin. And so that's very exciting. I hope some of you are going to be there. And if you are, definitely try to drop by the Tetrate booth. We're going to have a booth on the conference floor and come and say hello. We would love to see you. Peter, my colleague, is going to be there as well. So it would be great to meet you in person. And then separately, I'd like to cover just a list of Tetrate events that are coming up. Tetrate is going to host a co-located event at KubeCon known as the Service Mesh Immersion Day. That's Monday, May the 16th. It's a free event that you can register for free. Just go onto the Tetrate website and basically, go to the events page and basically click on register button. We also are going to run another instance of our Istio 0 to 60 workshop, which is very popular. A colleague of mine is going to be running that workshop on May 18th. That's Wednesday. And what else? And then next week, where I'm going to do a KubeCon report, episode 7. So that's what's going on with events. And all right, so that's it for announcements. Thank you, Adam, for being so patient with me and for covering for me while while I was having some technical difficulties. And what I'd like to do is introduce Adam more properly. Adam is a principal software development engineer at Workday. Workday is a fairly large company, but I know that they're active around both the service mesh tech stack. I believe Workday has using Istio in production. There's a talk on YouTube that I'm going to give you the link to. But this subject is not so much about Istio, but more about Envoy and Kafka. It's going to be a deep technical dive. I'm personally really eager to hear about it, simply because usually when we think about Envoy, we sort of jump to the more well-known use case of proxying HTTP traffic. But Envoy is a very capable proxy server that can proxy all kinds of TCP traffic as well. And so, as I mentioned this last bit, I'm going to sort of segue this and let Adam take over. So, Adam, welcome to our show. Would you like to introduce yourself before we begin?
Yeah, so hi, I am Adam Kotwasinski. I am a software developer at Workday. Our team is responsible for various messaging and persistence solutions. We handle Kafka, RabbitMQ, Redis, and so on. During my work, I have created the Kafka broker filters and Kafka mesh filter at Envoy, as we would want to investigate whether Envoy could act as a proxy for something actually different than HTTP, something that has its own custom protocol, namely Kafka. So we are going to have a presentation and some demos.
Wonderful. I'm going to go ahead and add your presentation to the stream and let you take it away from here.
Yeah, let's start. So this is the front slide. I have already introduced myself. I mean, the avatar is the one that I like. And the presentation is going to be separated into like 5 different steps. First, we are going to talk a little about what is Kafka. Then we are going to cover like how to proxy Kafka in a generic fashion, because Kafka has its own magical protocol, smart clients that need some extra handling. Then we are going to have a small example of how to use Envoy as a Kafka proxy. Then actually we will get to cover my work, namely the broker filter and the mesh filter. Both of these sections are going to have a pre-recorded demo. So actually, let's get to what is Kafka. I mean, right now we can see that the name is pretty popular. It appears in job offers pretty often. Like multiple companies use this technology. So basically, Kafka is a streaming solution for sending and receiving records. The records are stored in topics that are hosted by Kafka Clusters. And these topics are divided into multiple partitions. And the partitions are the basic unit of work assignment for producers and consumers. A single consumer can consume from multiple partitions. So far, nothing special. Basically, it's yet another technology for sending some messages upstream and then receiving the records from somewhere. So not much difference compared to other messaging solutions. However, Kafka has some benefits that actually lean towards the wide adoption. One of the things is like Kafka provides high throughput. So on the server side and for example, the implementation of the server is zero copy, namely that the byte arrays that are received by the server code are mem-copied explicitly into disk instead of doing any kind of transformations and so on. So like if producers send something called a record batch for a partition, like it gets picked up immediately and persisted on disk like that. Given that the Kafka clients are smart enough, then the server that would serve these records would send them out and have them processed correctly by the clients. Another thing that actually makes a difference from other typical solutions is like a reading capability. A record can be read multiple times, unlike typical messaging solutions where actually messages disappear after being read. It has its drawbacks, it has its benefits because it leans towards a bit different use cases. And Kafka is well known for its durability. The partitions are, we have partition replication where a single partition can be replicated across multiple clusters. It's called a replicate. Basically it's controlled by something called a replication factor. And given that messages do not disappear, records do not disappear after being consumed by the consumers, then we have both time and size-based retention configuration, which actually purges these messages after some time. For example, default configuration for Kafka is, I think, 7 days. Also, we have a concept of partition compaction, topic compaction, where the messages actually can overwrite one another somehow. So like, let's switch to these capabilities. Given what was said in the previous slide, we have some examples that are best described on Kafka website, but let's have a quick overview of them. Like, first and foremost, we can use Kafka basically as a messaging solution where we treat records as messages. We somehow use topics in a fashion similar to queues, and then we actually use other Kafka mechanisms to remember what messages have been consumed so far. So this actually simulates of how it would, this typical messaging behavior. The other solutions are a bit more leaning towards the thick pipe of data that Kafka is so well known for. Like, for example, website activity tracking, where we would want to have some topics that are composed of multiple partitions where we track each activity type, like on our website. And given that our websites are popular, then we would have very, very high volumes, and Kafka greatly leans towards itself. Another solution is, for example, a thick metrics pipeline, where all of the services in our stack emit metrics to unified record queues, record top partitions to store the metrics and have them processed later on, consumed by some services that would do the aggregation, plotting, and so on. Similar to metrics, we also have log aggregation, where actually instead of working with files explicitly and having them collected, we could have services that would write the logs immediately to Kafka and then have that aggregated. And given that Kafka is durable, we can actually rely on durable. We can switch to the last possible use case, external commit log, something like a transaction log, where we would store some kind of list of changes. And given that Kafka also allows random access, we could read the messages at any time and so on. Right. So given that Kafka is so popular, it has spanned a pretty rich ecosystem around itself. Like, first, we have raw clients like that are supported by Apache Kafka community. Official ones are, as far as I know, the Java Apache Kafka client that is also going to be used later in the demos. We also have librd Kafka for C and C++ that I use in Envoy filter. And also there are other client libraries for other programming languages. Some of them actually use the C++ at the bottom. And given that Kafka is popular, then we can see that actually it has spanned multiple wrappers or frameworks around itself, such as there is support for Kafka in Spring Kafka, we have Alpaca, we have Small Rye. And like, so far I have talked about producers and consumers that are pretty simple objects, but Kafka also has something called Kafka Streams API that provides us with a stream-friendly DSL that provides this good stream-like functions like mapping, grouping by, doing joins in memory, and so on. So this allows for easier implementation of our streaming services. And as a final requirement, then there is something called Kafka Connect, which is basically a framework service for defining source and sink connectors, where we could configure our application, our Kafka Connect application, with some ingesters or emitters, where we would connect to third-party solutions such as Redis, SQL, Hadoop, where we actually pointed at some kind of service, let's say Redis, and the magic would happen. We would read the keys and transform them into Kafka records to be put into some topics. And then we would have another connector that would actually read from Kafka, another instance, and put that into Hadoop, for example. So let's actually get into technicals, like regarding durability. What is a Kafka cluster? Kafka cluster is a collection of at least one Kafka broker that are going to store the partitions, and the topic is composed of one or more partitions. In this simple slide, we see three Kafka brokers that host two topics, one composed of three partitions, the other one composed of two partitions. They have different replication factors. Some of the partitions are called partition leaders, that are the ones that receive the produce and fetch requests from producers and consumers, respectively. And they are the main ones that handle this request. The other, actually, the brokers, simply replicate the data that has been committed by continuously fetching the payloads. This will be important when we are going to be proxying this further on. So now let's take a look into what is our partition. And actually, the abstraction here is not very complex. A partition is effectively an append-only record list. Producers effectively only append records at the end of partition, like we can see here in this example. And consumers actually can consume from any offset. It's not like you read from the end only, like in messaging. You actually can seek to any offset. So what is our record in that? From our perspective, it's only a triple of three entries. It's something called a key, value, and some headers that were added in Kafka 1.0, if I remember correctly. So something not very much different from a typical messaging interface. So now if we take a look into Kafka Producer, as we would want to send some messages to some records to Kafka, as we remember, we are only adding records at the end of partition. The producers are pretty smart, as in they have configurable batching capabilities. So this allows for even more throughput. So if in our, let's say, Java API, we actually provide multiple records to be sent to the producer, it's going to linger for a moment. It's all configurable and send all the records as a one payload and as a one request, what obviously saves us some performance. Again, given that the usual implementations of something called a partitioner allows us to control which partition the message is going to end up on, the typical scenario, like with Kafka, is that the API can either use the developers can explicitly provide the partition to be sent to, or we can use something called key-based resolution, where actually the value is computed from keys hash, at least for the default partitioner, that again can be configurable. And the latter two cases are going to be important for our mesh filter proxy, as to make these decisions, like if if the users do not provide the partition number explicitly, then we are going to need to provide enough information to the clients, like, for example, how many partitions are in the topic. And regarding reliability, as a producer, we can wait for some time until the message is actually persisted to the log on the cluster. So this is configurable by something called ax property. We can wait by default whether only the leader replica replies, or we can, for example, wait until the message has been fully replicated across all replicas. Or on the other hand, if we don't care about this reliability that much, we can simply wait for no confirmation. As a bonus, also, Kafka Producers provide some kind of transaction and idempotence capabilities. So we can configure it to, on the idempotence side, we can configure it to have exactly once delivery semantics without any so actually, even if retries happen due to network outages, the message would have been persisted only once. There is also the transaction APIs where we can actually submit multiple records as a single transaction to the Kafka cluster. So now if we switch to the consumer, actually, it's again a simple object that is capable of consuming records from particular partitions. We can consume, as our developers, we need to consume, we need to specify which partitions we want to consume from. The partition assignment can be either explicit, we basically tell what partition numbers we want to use, let's say topic A, partition 13, or it can be cluster managed where we subscribe to particular topic, let's say topic A, and we wait for the cluster to assign us partitions because we are going to use the consumer group feature that is going to be covered later on. And the important part is that if we follow up this idea of Kafka partition being basically a giant remote byte array, record array, then we can, the consumers can actually receive the messages from any offset. There is seek API where we can basically tell the consumer, move to offset, let's say 100, and start receiving messages from that offset. So as you can see, this allows us to implement services that would basically read from any predefined offset, and then our business logic could be implemented this way. So I mentioned something called consumer groups that are one of the cool Kafka features. It allows some kind of load balancing across multiple consumers that we can see here in this slide, like with consumer property, consumer group value, all consumers that are members of this have the same consumer group value are going to have the partitions distributed among the group members. So if, like we see the example at the bottom, like we have a topic with 5 partitions, and we have one consumer group that is composed of 3 members. So these 5 partitions are going to spread across these consumers. And the other consumer group 2, that has the red arrows, it has only 2 members. And again, these partitions are distributed among these members of this group. So, I mean, this feature is nice and useful in a fashion like it's all managed by Kafka magic in general. Like there is auto balancing that is configurable. If that manages also the partition assignment, which consumers can be are going to consume which partitions, and it manages the group membership in a reliable fashion, as in like we handle new consumers joining, we handle whether new consumers die or don't respond to heartbeat request, internal heartbeats for long enough. So this is how it allows us to quite transparently distribute the load among the services. So again, the last feature is like we have consumer offsets. Like we have these consumers where we actually have received some records, but now we can actually save which messages we have consumed. We can use Kafka for that. There is an internal topic called consumer offsets, or we can track it on our own in our own persistence. Effectively, a consumer offset is a triple of group name partition and the offset that we want to save. In Java, for example, we have API for that, for synchronous, asynchronous committing of these offsets. We also have the property that controls the automagical saving of these offsets as long as the consumer is alive. And this implies also delivery semantics that we can have in our Kafka consumers. We can have at most delivery where the offset is committed before it is processed at least once, when we actually have offset committed after it is processed, and exactly once, which is a bit more complex, like we have the transaction API that also allows saving offsets as a part of transaction. Or if we want to have like business logic, like some extra external business logic transactions, we then need to actually store offset in an external system together with the process data. So either or, we save the offset and process data, or we roll back the whole transaction and hope that we would receive the message again after the restart. So so far I have talked about actually what Kafka can do, but now let's get into a bit lower into the Kafka protocol. So the protocol is pretty simple. What's important here is that actually the Kafka clients are pretty smart, as in like it's not a simple TCP connection like a Kafka consumer, Kafka objects, producers, consumers, admin clients to perform its duties actually need to negotiate the protocol first with Kafka clusters. So they can exchange the information about API versions, what kind of requests are understood by both sides. This also allows back compatibility between different versions of clients and servers, as long as the API matches. So for example, there is no problem using a 1.1 client with 3.0 servers and vice versa. And another part, after we have established the protocol, we can really have the automatic discovery of cluster members. It is achieved through metadata requests and responses, where the clients actually reach out upstream asking, how does the cluster look like? What topics are present in the cluster? How many partitions are in the topics? Which brokers actually are the leaders for these topics, and which brokers are replicas? And actually the final part, where are the brokers? What are their hosts? What are their ports? So this allows then these clients to make the connections upstream to the correct brokers that handle the data and so on. So here we have a simple drawing where actually we have a Kafka cluster that's composed of 3 brokers and that they are all managed by the same zookeeper for now, craft implementation in future. And we can see it making a metadata request and then having a response that basically tells us that there are some topics and there are 3 brokers that are achievable. Shri, no, I will not be covering ACLs. But I think that should be with Kafka client Envoy. ACLs might then, it feels like it could be a future implementation of something in a broker filter or the mesh filter, but let's cover it later. Regarding proxying Kafka, so now we have covered what Kafka is doing. So we would want to put some kind of proxy in the beginning, in front of the cluster. So given that the protocol is smart, we need to actually make the connections that the future client is going to make to go through advertised, to go to proxy instead of going to the brokers immediately. And fortunately, it is supported by Kafka servers themselves. The Kafka servers have a property called advertised listeners that actually tell the clients where to connect to. So actually, then in our proxy, we need to start listening on a particular socket. And in our Kafka server configuration, we need to actually advertise the proxy socket, not the one that the Kafka broker will be listening on. So effectively, this means we need to have this configuration in both sides of the deployment. And this scenario is not Envoy specific. You need to do that with any kind of proxying, or whether you use Envoy, Nginx, or whatever. So if we were to do that, then it would work, as in the Kafka client traffic would go, in this example, for example, to port 19092, be proxied by proxy to port 9092 and reach the Kafka broker, the response would be sent, and it's all good and fine. However, the problem is that the Kafka brokers communicate with each other. So actually, the replication is handled by the Kafka brokers sending the fetch requests from one to another all the time, basically. And that would also go through the proxy, what might not be what we want. So there is a solution for that. Again, the Kafka server allows for configuring something called interbroker listener name, where we would configure that the traffic between the brokers would go on a different interface, on a different socket. So this allows us to use the proxy only from the downstream traffic, not the internal one. So given that we have talked a little about Kafka, how to proxy Kafka, now we can finally switch to Envoy as a Kafka proxy where we would use Envoy. So let's have a very simple example where first we are going to use Envoy's pre-built TCP filters only for proxying. So in general, if we have a cluster composed of n brokers, then we would need to provide as many listeners in Envoy, whether it is going to be a single instance or multiple instances, one of them, each of them handling only one listener. We need to provide as many listeners as there are brokers. And again, each of the listeners would then use the TCP proxy filter to point to the upstream Kafka broker. In Envoy configuration, that would be represented by something called Envoy Cluster configuration object, but this time I'm talking about Envoy Cluster, not the Kafka cluster. Unfortunately, the vocabulary can be a little confusing. And then we have the filter chain that could be theoretically enhanced by some extra additions, where we would have, for example, local rate limiting and so on, TLS termination, where we would have the features provided by existing Envoy filters. So to sum up, we are going to have a one-on-one mapping, one listener in Envoy and one broker somewhere, and bound to each other by the configuration that matches each other in the end. So if we take a look at this example, Envoy config, we have a single Envoy instance that is proxying two Kafka brokers. We can see that two listeners, one named L1 that is listening on a socket 19092, and we can see that it has the filter chain that is pointing to cluster C1. And again, this cluster C1, if we follow the orange arrows, is pointing to the host, to broker 1. And this is the broker 1 configuration on the right side, where we actually see the broker ID 1, and we can see that the socket that the broker instance is listening on, and we can see that it advertises the socket that Envoy is listening on. So this is how the traffic goes. Again, we see the other listener, the listener L2, again at the top with the blue arrows that is doing the same thing, just with the other broker. So this is a very simple scenario how to proxy Kafka with Envoy TCP filter. Again, we have this filter chain, so then again, we could put something in front of these filters to provide extra capabilities. It is up to the people managing the clusters, the installations of what kind of features would they want from proxy installation this time. So now we actually have a very simple filter chain. So why not enhance it and use the fact that we could, for example, parse Envoy Kafka Protocol, which is again some kind of TCP stuff going on between the client and the broker. But first we need to actually understand what are the requests and responses flying on the wire. So the first thing I had to do is to create some kind of serialization code that would take the byte arrays we receive in Envoy filters and transform them into request and response objects. So with a lot of help from Mr. Matt Klein from Envoy, I managed to deliver that. So starting at the bottom, like Kafka message files are fortunately defined in language agnostic fashion. There are some JSON files that describe what kind of headers, what kind of fields are present in a message, in requests and responses. So with that, I had to create some kind of Python code that would process these definition files and generate corresponding C++ code, mostly headers, that represent the Kafka requests, such as API requests, metadata requests, and so on. And like, if we take a deeper look into how the message looks like, we can see that the Kafka messages have increasing correlation ID, basically the communication on the connection that the downstream client makes to the upstream Kafka. Each message has a continuously increasing message ID. There are, for example, we can see if we implement stuff badly that there is a possibility for out of order errors and this kind of stuff. But with this correlation ID, we can have matching between the request and the response. And in future, in the next slides, we can actually match the request. Thus, for a HTTP stream, I'm not that familiar with Envoy HTTP connection manager.
Yeah, I'm sorry to interrupt. So the question is, the connection manager for HTTP parses the TCP stream for anything that's layer 7, the headers and things like that. And it sounds from your description
it does.
Okay.
It does.
That's awesome. All right.
Yeah.
You provide a higher level of information through this parsing.
Yes.
Okay. Sorry to interrupt. All right. Sorry, carry on.
No worries. Right. So then actually we have these numbers, and in future in the broker filter, for example, we can use them to track when a request was received. And then when we finally get the response, we can match that timestamp and get the processing time metrics. Also, the newer version of requests contain something called the Kafka client ID identifier, a property that is again configurable in the user space land, like in Kafka Producers, Consumers. So this property of a record of a request is available basically as an STD string. So given that now we have the serializer code, we could create the Kafka broker filter providing this feature. So it's an intermediary filter intended to be used in a filter chain before the TCP filter that sends the traffic to the upstream broker. Right now, we do not do any kind of modification on the data. We basically take data as it is and send it upstream. However, we process it. We capture the numbers of how many requests, responses we have received and the request processing time. And given that it's all code and it's implemented, it basically proves to be an entry point for future features for like per connection concepts like ACLs, for example. We have the client ID, so why not in future some developer would take this code, take this string client ID and pass it to some kind of authentication backend, and then, for example, close the connection if something does not match. However, it's all up for extension. So let's go. So now I am going to start a very simple broker filter demo where we are going to see how it works. We are going to start a Java application. Now okay.
Do I need to add it? Yeah, let me go ahead and add it for you.
In this Envoy broker filter demo, we are going to have a very simple topology with a single Kafka cluster composed of 3 brokers and a single Envoy instance that is going to be the proxy for them. In the configuration, we can see that brokers are listening on a single socket, but they are going to be advertising the Envoy socket. The interbroker traffic is not going to be proxied. Similar configuration happens to be for broker 2 and for broker 3. In Envoy, we can see that there are 3 listeners as there are 3 brokers. Each of them has its own listener socket. And starting at the bottom of the filter chain, we have a TCP proxy filter that's pointing to the Envoy cluster corresponding to the single broker instance and our Kafka broker filter. In our test scenario, we are going to point our producers and consumers at Envoy instance. We are going to create a consumer, gets its current position. Then we are going to create a producer, send some record. Then as a consumer, we are going to receive that record. We are going to send fetch requests until we receive the message. Then we are going to verify whether the record sent was the one that was received. And finally, we are going to shut down and commit our offsets. So let's run the scenario. Fortunately, it has succeeded. Let's have a look into the logs. We can see what was mentioned in the previous slides, that the first part of interaction between any Kafka consumer producer is figuring out at the in the protocol, so we can see the API versions, requests, and response coming back. Then we have the metadata, and we can see that the nodes are appearing in the metadata response. We can see that it's the advertised port that's visible here. So finally, when a lot of this negotiation happens, the consumer will manage to get its current position after the group membership and so on has been resolved. Finally, we get the offset fetch request and its response, and that was passed to our Java code and printed out. Then, as a producer, we again need to go the same way. We need to figure out the protocol, and in the end, we are going to send the produce request. We can see it here, and we can see that it was sent to node 103. Later on, the consumer is going to poll for the records. We can see that it sends the fetch request, it receives the records. Finally, the consumer shuts down and commits its offsets. So we saw that the producer sent the request to node 103. So now we can take a look into Envoy metrics. Given that node 103 was remembered with prefix 3, we can see that somewhere here we should see the produce request. Yes, it is here, and there should be the produce response. Of course, the same thing happens with the fetches. We need to remember that a single poll invocation in Java client, for example, does not mean it's only a single fetch. It's configurable, and the consumer is going to send fetches as long as the timeout permits. If we run this scenario a few more times, then the histogram metrics for the processing duration should finally fill up. So 1, 2, 3 cases. And we can see prefix 3 again. We have finally sent 4 requests, and at the bottom we can see the histograms of how much time was taken for each of the request and response times. Now let's switch to the other scenario that I had, just to show you other APIs that are possible with Kafka. For example, we have admin operations with something called admin client. We are going to create a topic, then we are going to list the topics, then we are going to delete a topic, just for the sake of it. So let's run it. Right, it fortunately succeeded. Let's have another look into our logs. We can see the same thing. We wanted to create a topic, but to create a topic, we need to understand the API versions, the metadata. But finally, we can see that the create topics request was emitted and the response was received. Then we listed the topics, and it's an interesting implementation detail that listing topics is actually achieved with metadata requests, and we basically send the request for the null array of topics. Then we receive the response of all the topics partitions that are present in the cluster. Finally, we requested for the topic to be deleted. We sent the request, and then we got the response that it succeeded. And in the end, this concludes our work. We can also take a look in the metrics, and there should be the corresponding entry for the broker that was visible here. We should look for node 101. So it means prefix 1. And we can see the delete topics request. And this finally concludes our demo for the Envoy broker filter.
I'm back.
Very interesting.
All right.
So it's really amazing. I've got some questions for you about. Are you already building dashboards to be able to consume those metrics, or? Or is
my
that the next step?
development,
I don't know what.
in my development installations. However, when you Google for that, I think one of the companies called TransferWise at least mentioned the broker filter somewhere.
Nice.
And also I remember that some other company that also does some kind of mesh services also uses that to collect metrics. So then again, we have Envoy metrics. Do whatever you need to do with them.
That's right. Yeah. It's there. It's exposed. It's gonna. Yes. You can. Yeah.
Right.
Very nice. Carry on.
Thanks. Right. So now we have covered the broker filter. So that, after all, it was nice. It allowed us to understand the protocol, collect some metrics, provide an entry point. But it's something very tightly coupled to Kafka itself. We need to create a listener instance per broker, and it actually doesn't. All the magic actually still happens between the downstream client and upstream Kafka server. So why not actually create something called the Kafka mesh filter that would abstract out much more? So that's actually what I am going to cover right now. We are going to cover the producer mesh filter, where we are going to receive and process requests coming from downstream producers. And we are going to have a single Envoy listener that is going to send multiple records to multiple upstreams, to multiple upstream Kafka clusters. So what was actual motivation for this work? I had a situation when we had so many clusters that managing the configuration of downstream clients was starting to become a hassle. Also, I would like to introduce some kind of single control point where the traffic would be routed through, and possibly in future provide some kind of extension point to introduce some custom logic into that. So with that, the Envoy mesh filter was created, where the Envoy is simply acting as a facade for multiple Kafka clusters. The downstream clients would not be aware of what the Kafka clusters upstream are. Envoy would perform the necessary traffic routing, and the received Kafka, yes, I am decoupling them. Received Kafka requests would be routed to correct clusters depending on a filter configuration. So Envoy Kafka mesh filter is effectively a terminal filter in Envoy filter chain. That is the link to the configuration. From the client perspective, we connect only to Envoy. The Envoy instance in this level acts effectively as a Kafka broker in a one broker cluster. The upstream connections that the Envoy makes to the Kafka clusters are done with embedded Liberty Kafka producers. I also have on my own article on Medium that actually describes it in a bit more detail and how to deploy it. So it's Googleable. So effectively, in a picture format of what I have described, at the bottom, we can see the Kafka producers that would be connecting to Envoy listener sockets, would be handled by worker threads. The records would be received. They would be passed to forwarding rules that would then decide, depending on the configuration, which upstream cluster to send the data to using the embedded Liberty Kafka producers. And we can see that we have a producer for each of the upstream clusters. These are different, separate clusters this time. So we are actually proxying multiple things. So how would the typical flow would look like from the internal perspective? Like filter instance pretends to be a broker in a single broker cluster. And this means that it needs to be capable of handling the API and metadata requests. When any kind of partitions topics are queried by the downstream clients, all of these partitions, the response say that all of this data is simply hosted by this Envoy instance, basically. When the producer requests are finally received from the producers, we extract the records, then we push these records to our forwarding rules, and then depending on the decision, we submit them to Kafka, to Liberty Kafka producers, send them up to the top, and again, filter the Liberty Kafka producers wait for the delivery responses of any kind, basically, whether it's an offset data at which offset the record has been saved, or whether it actually failed. I mean, on our level, it doesn't matter too much. We aggregate these responses and send them back downstream. So given that it's a complex mesh filter scenario at this stage, where there were some challenges, for example, implementing these API versions metadata requests. So for API versions, I had to implement to provide a response of what kind of requests are actually understood. Basically, right now, the Envoy mesh filter supports only 3 kinds of requests. Basically, effectively, API versions, which is the step 1 in communication, that we understand some part of protocol. We understand API requests, actually. We understand metadata requests and produce requests. We had to implement the we need to handle the metadata requests to actually make the client send all the traffic back to Envoy. And we also need to handle the produce requests coming from producers. Nothing more at this stage, but again, it's extensible and could be implemented in future. There was a very interesting trick in metadata response, like given that we need to, our Envoy instance behaves just like a broker effectively, we also need to provide something similar to metadata response our host and port to make the clients make the second connection to us. So I introduced 2 configuration properties to Envoy to the mesh filter configuration, so they could be provided. Same thing with partition numbers. So this is a required configuration for each of the upstream clusters that we are going to connect to. This data is used by, and maybe you noticed that before, this data is going to be used by producers that is the default partitioner if they do not specify neither the explicit partition nor the key. In future, maybe this could be actually changed to something more reliable or easier to handle. For example, the Envoy would make the filters, make the connections upstream to figure out the topology of the cluster, the default configuration. However, right now we have the cheapest implementation where it's simply configured by a constant property. And now we have the forwarding policy. So right now we receive the producer request, and the producer request contains the record batch that is composed of multiple records. And each of the records contains the information which topics actually, topic partitions it should be sent to. Right now, the forwarding policy is very simple. Like we simply take a look at the prefix and we pick the first match in the filter. So it allows us to, for example, filter all topics, all records going to topics starting with letter A to go to cluster 1, and everything starting with letter B to another. So this is, again, a place where things could be extended and some kind of extra filter, extra decisions could be made. Basically, if you take a look into the Envoy mesh filter code, these are the places where there are headers where basically we make a decision, and there is the method that I actually mentioned that get the producer for the topic. And as an implementation detail, a single produce request, due to the fact that Kafka Producer can batch the records to be delivered due to its linear configuration and so on, we can actually receive a single request that contains multiple messages for multiple topics that map to multiple upstream clusters. And this is fine for us. I mean, all of these records can get pushed to forwarding policies and then sent upstream, and then we just need to wait for the responses. Then we aggregate them, obviously failures taking the priority over any kind of success information for each of the partitions. Also, we have embedded Liberty Kafka Producer that is going to do the real work for us. We're going to create an instance of Kafka Producer per internal worker thread. And as a bonus, we have these producers can have custom configurations, things typical for Liberty Kafka Producers, for example, args, buffer sizes, and so on. As the deployment diagram, the structure diagram at the bottom shows, starting at the bottom, we have a produce request holders that actually maps to, that references the upstream Kafka facade, that again references something called a thread local thread local Kafka facade that is bound to each Envoy worker. And this one actually contains references to the producers pointing to the cluster upstream. So this is actually the scaling factor. By changing the concurrency level on Envoy, we can create more or less Envoy Liberty Kafka producers. Okay, and now it's time for another demo. So I need to add it now and share a video file. Okay. Okay.
I see it. Yeah, I'll be adding it. Here we go.
In our Envoy Kafka mesh filter demo, we are going to have a very simple topology. We are going to have 3 Kafka clusters. Each of them is going to have only one broker. And we are going to have a single Envoy instance with the mesh filter that is going to have its own listening sockets. And it's going to have very simple forwarding rules. Basically, records that are sent for topics that start with letter A are going to be sent to cluster 1, with letter B to cluster 2, and with letter C to cluster 3. The broker configuration, the cluster configuration is nothing special. We basically have only 3 brokers that do not know anything about each other. They do not have any custom advertised listeners or anything. They are just standalone instances. However, the Envoy configuration is going to contain a lot. So basically, we have our socket where we are listening on, and this is where the Kafka clients are going to connect. And starting at the bottom, we have our Kafka mesh filter that basically acts as a Kafka broker. So we need to advertise ourselves just to fulfill the obligations that are specified by metadata contract. And we have the references to the Kafka clusters. Also, the clusters have varying value of default partition counts, as right now they are empty. They do not have any partitions, while we still need to respond to metadata requests. And just for the sake of it, the cluster 3 is going to have custom configuration that's going to be passed to the Liberty Kafka Producer. And also we have the forwarding rules that were described just a moment ago. Depending whether the topic starts with A, B, or C, then the messages are going to be sent to different topics. And because actually our Kafka mesh filter acts as a Kafka broker, then there is no problem setting up the Kafka broker filter in this filter chain. And this actually allows us to gather the metrics that are coming to and from the mesh filter itself, and it also allowed me to avoid, implementing the same thing twice, or even working around with sharing the code across 2 filters. So let's start our scenario. What are we going to do? We are going to point our producer at Envoy, right? Localhost 19092, and we are going to use 4 topics. You might notice that they start with A, B, C, and for each of these topics, we are going to send 10 messages. And just to make it a little tricky, we are going to use default partitioner. We are not going to set up the explicit partition. We are not going to provide the key. So the producer is going to depend on the metadata partition, the partition metadata, to figure out where it wants to send. So let's run the scenario. And we can see that it fortunately passed. So let's have a look into our broker data to see whether the messages were actually received. Here we have the MX4J view into our Kafka brokers, 3 clusters, and let's look for log and offsets. We can see that for the broker 1 in cluster 1, that is supposed to host topics apples and apricots, which were created, we can see that each of them received 10 messages. Now, in case of broker 1 in cluster 2, we should find the bananas topic. Yes, it is there with 2 partitions. Each of them has 5 messages. And in case of cluster 3, which is again only with only one broker, we have the cherries topic, log and offset. We can see that there are 5 partitions, and each of them received some messages. Again, given that we had the broker filter in our filter chain, we should also see these requests coming to our Envoy instance. So produce request. As we sent 10 messages per 4 topics, we got 40 produce requests. Also, we can see that in the beginning, there was the API versions request and metadata requests. 4 metadata requests, why? Because we were sending our records to 4 topics, one for apples, one for apricots, one for bananas, and one for cherries. At the bottom, again, we have the response metrics that the responses were received. Fortunately, the test passed. And we have the duration histograms. Now, if we take a look into our client logs, we can see actually a very similar situation to the previous demo. When we started our producer, we first had to figure out what is the protocol. So the protocol negotiation happened. We can see that actually the message unsupported appears here multiple times because obviously the mesh filter does not support most of the requests. Then the metadata appeared, where we were requesting the who is the leader for the apples topic, and we received the information that there is only one broker, our Envoy instance, that hosts the one partition as given by our configuration. Then we can see that the messages, the produce requests were sent and the responses were received. Something similar happened for apricots, also for bananas. In that case, we remember that bananas had 2 partitions. So we can see that sometimes they were delivered to partition 0, sometimes to partition 1. And very similar for cherries, just this time we had 5 partitions. And we can see that the partition decision was made by the client, but we managed to handle that because the way that Envoy's configuration matches the upstream cluster configuration. Now, if we take a look into our Envoy logs, we can see that we started our Envoy instance. We can see that the forwarding rules have been processed. And later on, when we started receiving the connections and requests, we could see that both the Envoy broker filter started logging that some data is being received. We finally received the producer request that was corresponding to our first request for Apple's topic. We can see the delivery is being finished, and finally us being ready to respond downstream that we have managed to forward the records. These are the correlation IDs that are also visible in the logs. So the same happens for all the 40 requests that we have performed over our demo. The last request appears to be producer request 45, and that should match what we have in our logs as well. Right, producer response and correlation ID equals to 45. So this way we have managed to configure our Envoy to act as a front proxy for 3 different clusters and use the forwarding rules to have the traffic from the downstream clients received, processed, pushed to forwarding rules, sent to correct matching Liberty Kafka producers, and therefore to upstream Kafka clusters. When the responses were received, when the actual Liberty Kafka producers finished their delivery, and fortunately it was successful in this scenario, we could respond to the downstream that we have finished with the delivery, and the offsets saved were the ones that were actually received from the Liberty Kafka producers. This concludes the demo.
Yeah.
That was, I must say, very powerful. I can't help but sort of air some of my thoughts. It seems to me like you've effectively extended Kafka in a manner that's completely decoupled from the Kafka code base.
Yes,
by
that is
leveraging the native capabilities of Envoy. That's just, it seems absolutely brilliant.
This is something very similar also, I mean, a different technology, a different TCP stack, like Matt Klein has done for Redis filter, right? I don't know the details, but he actually is capable of managing like multiple upstream installations, some kind of hashing, whatever. So yeah. There is still a lot of work to be done. And like, if you click on, let's say, Envoy documentation page, I left like 9 or 10 disclaimers of what doesn't work, what needs to be configured an extra way, because like many of these things can be improved, many of these things can be extended. Obviously, like I am doing the forwarding by the prefix of a topic, because I mean, in my scenarios, I use Kafka heavily as a messaging solution. So I have hundreds of topics that basically start with the same prefix. But then again, nothing should to stop us, for example, providing an implementation that does some kind of load balancing, bucketing, whatever, or even if we are feeling a bit adventurous, like mirroring producer, receive a produce request once, produce it to 2 clusters. So effectively have Envoy act as some kind of mirror maker. Again, it also what is needed is basically to sit down with IDE, start cracking out the code, and push it to the mainstream.
Yeah. I can see there's tons of possibilities. So, I mean, for those of us who are listening out there who are working with Kafka, I'm hoping this has piqued your interest, and you've got a foundation there that you can perhaps build on and add something to the implementation that matches your needs in terms of the way you're using Kafka.
Yes, because I mean, after all, it's a proxy, and like it's always an opinionated solution, right? Like it makes the decisions that the implementer made to suit them, but maybe they would have other goals for the future. So then it ends up having a configuration that has plenty of toggles all around, and like how would you actually want to receive that? A bit of a problem around this is that to use this proxy, you need to more or less understand how Kafka works. It's like it's not trivial, unfortunately, at least not yet. It's not like bulletproof.
Yeah, understood.
Yeah. So we have a bit more slides.
Okay, go for it.
Yeah. Are you sharing them? Oh, okay, thank you. So, right, we have covered what is implemented right now, but I would want to cover what I would want to create in the future. So basically a Kafka mesh filter for the consumers. So like we have managed to handle the producer sending the traffic and it getting sent upstream. But I would want to allow the consumer to use Envoy as a single entry point to consume data from multiple upstreams. But given that it's a work in progress, I mean, we can have 2 consumer types. So on the left-hand side, we have the shared consumer concept, where Envoy would have a similar implementation to what is now for the producer. We would have a single consumer instance that would handle multiple fetch requests coming from multiple downstream clients. So this means for a single request, we would actually a single fetch request would map to a multiple fetch requests would map to a single consumer, and the default implementation would then somehow result in something like messages being received by that Liberty Kafka consumer to be distributed among the downstream connections. This would be somewhat similar to what is provided right now in Kafka REST proxy, just not for HTTP, but for pure Kafka protocol. And again, it's somewhat similar to Kafka consumer groups. All the consumers that would connect to Envoy filter would have the messages distributed, but without all this, handling of partition assignment, communication, and so on. So this is one possible future implementation. The other future implementation is something more naive, a dedicated consumer downstream connection, where we would create one in Liberty Kafka. So this would allow us to have a more Kafka typical behavior, less opinionated, less magical, where multiple connections, for example, receive the same message. it is possible that the consumer group support could be then handled. Basically, we would need to implement a lot of Kafka client protocol regarding the joining groups and so on, and somehow translate that into the consumer that would then need to connect to upstream clusters. So again, these are two things that could be implemented. Still, it's up in the air. So this concludes what is planned for the future. Again, there are some improvements that have been mentioned before. So like nothing is committed to, but contributions are very welcome. So that's it.
Adam, I want to say I really appreciate you sharing all of this work with the community. Sometimes it helps to expose something because there's just so much information out there. And I hope that folks find this useful and can maybe contribute to this project.
Yeah, and like I don't have much more to say. I mean, I don't know if there are any questions.
Of course. Yeah, I'm monitoring the comments right now. They've been relatively sparse. I think the last one was the question from Shri, and a couple that I had asked actually, because that was really by some of the things you were demonstrating. Anyone? I guess this is last chance for anyone to chime in. If you have your burning questions, please don't be afraid to ask them, and you don't have to reserve them to the end either.
Or alternatively, if something appears later on, feel free to ping me somewhere on Envoy Slack or Envoy GitHub. Basically, there is, I think, that even a label for ARIA Kafka, so things could be discussed there. But then again, discussing is easy, the implementation is hard. So that's the tricky part.
And I'd be happy if you send me some of the links from your presentations. I will add them to our Tech Talks landing page so folks can go to your blog entries and can get to those resources. Wonderful. Well, thank you so much for your time, Adam. I'm going to, as usual, wrap up our episode with just kind of a look ahead real quick. Basically, the one thing I wanted to mention is if you're curious about how large enterprises use Istio, so this is beyond Envoy, I noticed on the Istio YouTube channel, there's a Istio community playlist with a talk by Cathal Conroy about scaling Istio as they moved to production. So that was an interesting talk. It has nothing to do with Envoy and Kafka, but I guess the common point is activity around proxy and service mesh at Workday, which I found interesting. So if you find that something worthwhile pursuing, the link is right there on that page. Next week we'll be doing a report of everything we will have learned at KubeCon EU. So stay tuned for that. And just a reminder that if you're interested in getting a certification for Istio, that we offer also a 30% off coupon. If you're interested, go ahead and note that or reach out to us on the Tetrate Slack, which is my last sort of piece of news. Tetrate has a community Slack that I urge you to join and reach out with any questions if you're looking for that coupon code, or if you have questions about the certification or other things about this talk that we just listened to. You can also start a conversation around that there. And just want to tell everybody, thank you for your time and thank you for listening in. And we'll see you next week in our next episode. All right. Bye, Adam.
Cheers. Take care.